Welcome to another session of spectroscopy or analytical techniques. Today we are going to look into colorimetric analysis, which is also called as colorimetry, which is nothing but spectrophotometer. Before we move on, subscribe for more informative videos. At the end of the session, you'll be able to state the principle of colorimetric analysis, explain the instrumentation of colorimetric analysis, estimate the unknown concentration of a given sample, and also list out the applications of colorimetric analysis. Colorimetric analysis is used to determine the concentration of the substances that absorb light in the visible region, that is, the wavelength between 400 to 800 nanometers, or to be more specific, 400 to 750 nanometers, by measuring the intensity of light, which depends on the intensity of the color. So this obeys for colored solutions only. If the solution is not colored, we need to make it colored by using a complexing agent or coloring agent, and this obeys B. Lambert's law. Let us look into the outline of the instrumentation of colorimetric analysis. This is a tungsten lamp, which is a source of visible light, that is, it supplies light between 400 to 750 nanometers or 400 to 800 nanometers. And we use a collimator, that is nothing but a lens which narrows down the beam and aligns the light. And here the light which is aligned is passed through an entrance slit, that is, a narrow beam of white light enters the entrance slit, and this whole setup we call it as a monochromator. What is the role of a monochromator? It absorbs all the light except the chosen light, that is chosen wavelength. We choose one particular wavelength depending on the absorbing substance. So here we have taken a prism. We can also take a diffraction grating. So this splits or disperses the white light into visible spectrum, that is our VIBGR. Now through the exit slit only the chosen wavelength comes out and all the other wavelengths are absorbed depending on the absorbing substance. We'll come back to this when we are analyzing the sample. If you look at this part, the intensity of light passes through the absorbing substance. Depending on the concentration of the absorbing substance, some amount of light is absorbed and the remaining light comes out, that is the transmitted light. If you look at, this is the part we have already discussed in B. Lambert's law, that is our previous session, that is I naught enters the absorbing substance and the remaining light, intensity of transmitted light I, comes out of the solution. Now we use a detector to detect the intensity of the transmitted light. A photocell is normally used, which generates current proportional to the intensity of the transmitted light. But here we don't want the intensity of transmitted light, but we want to know the absorbance. That is, in our previous session, that is B. Lambert's law, we have seen A is equal to log of I naught by I. So this instrument calculates that absorbance value and gives you the absorbance value. But we have a choice of even selecting transmittance, but here we are more comfortable with the absorbance value. The meter displays the absorbance value. What we have discussed, we have just given in statements. Source supplies the light of visible range. Collimator narrows down and aligns the beam of light. Monochromator allows only the chosen wavelength. A prism or a diffraction grating can be used. Cell, here that is it which is holding the sample. It's very important that the cell should not absorb any light. It should transmit all the light which is entering into it. And the detector detects the intensity of the transmitted light coming out of the cell and generates current proportional to it. We use a photocell normally, and the meter displays the absorbance value or the transmittance value depending on what we have chosen. Here, how to determine the unknown concentration of the given sample. For this example, we have taken iron, that is Fe2 3 plus concentration. Here I have chosen the Algerian font, which is not giving E as a small letter. It should be Fe. E should be smaller. We'll see the procedure to be done. First, we need to have a blank sample and a series of known concentration. If we are going to analyze Fe3 plus ions, we can take any of the ferric salt. It can be ferric chloride or ferric nitrate. So here we have taken ferric chloride solution, but ferric chloride solution is not colored, so we use a complexing agent. So we can use potassium thiocyanate or ammonium thiocyanate. When we add this to it, we get ferric thiocyanate, which is blood red in color. So now the uncolored sample is made to colored, where we need to have a blank sample. Blank sample contains a solvent which is used to prepare these solutions. Here we are using water, so our blank sample becomes water. We need to take water in this, and we should not have any of the absorbing substance. Here our absorbing substance is ferric chloride, so we should not have ferric chloride solution in the blank sample. And we need to add ferric chloride solution in increasing concentration in all these. That is, we are going to increase the concentration of ferric chloride when we start from this cuvette to this cuvette. And now we add the complexing agent, that is potassium thiocyanate. Constantly we need to add the same amount of potassium thiocyanate into all the cuvettes. Okay, now as the concentration of ferric chloride is increasing, the intensity of the color is also increasing here. Now this is how we prepare the blank sample and a series of known concentrations of ferric chloride sample. Here, why we are adding the complexing agent into the blank sample? It is very essential, because not only blank sample, if you're adding any of the additives for any other analysis also, all the additives should be added to the blank sample except the ions to be analyzed. This is because if any impurities are present in any of the additives which absorb the light which is chosen, that is the wavelength which we have chosen, it will be nullified, because we are using the same water and same additives in all the cuvettes, because we want to analyze only the ferric ions and nothing else should interfere in our analysis. This is how you prepare the series of samples. Now, because we are using we are going to analyze ferric ions. Here the wavelength chosen should be 480 nanometers, because this absorbs a wavelength of 480 nanometers. In our previous session, I have told you how to choose this wavelength. This wavelength will be the wavelength which has epsilon value to be maximum. A is equal to epsilon CL, where epsilon is maximum. That wavelength is generally chosen, so that the sample is very sensitive to that wavelength. In the monochrome matter, we are going to choose 480 nanometer. Now we should place the blank sample in the cell holder and set the absorbance to 0. Now only I said, if any impurities are present in any of the additives or even the water, it will be nullified, because we are not taking any of ferric chloride's solution in this first blank sample. So we set the absorbance value to 0. And now the experiment becomes very simple. We need to set the series of samples. We are placing one by one in the same cell holder, and the absorbance values are noted. We need not disturb the setup. That is, we have blank sample, we have set the absorbance value to 0 and different concentration, that is C1, C2, C3, C4, C5, and we are going to note down the absorbance value A1, A2, A3, A4, A5. And we draw the calibration graph, that is absorbance versus concentration. We are having concentration on the x-axis and absorbance on the y-axis. We have the calibration graph which passes through the origin. Why it's passing through the origin? Because when the concentration is 0, the absorbance was set to 0 by us, so it passes through the origin. We have different concentrations. As the concentration increases, more will be the absorbance, because the light is absorbed and it passes through the origin. Already in the previous session I have said, at higher concentration it becomes non-linear, so it is more suitable for lower concentrations. Once we have the calibration graph, now we can identify the concentration of the unknown sample. That is, all we have to do is place the unknown sample, that is the unknown concentration, in the same cuvette. Why we are placing in the same cuvette? This path length becomes constant, that is width of the cuvette is same because we are using the same cuvette, and epsilon is constant, so the absorbance is proportional to only the concentration of the solution. Now we place the unknown concentration in the same cuvette and measure the absorbance value from the meter. Once we have noted down the absorbance value, come back to your calibration graph, go to your absorbance value, go to your linear line and pull down the line to the x-axis, that is Cu. This becomes your unknown concentration. This is very useful in industries where we have plenty of samples to be analyzed daily on day-to-day basis. So monthly ones or weekly ones, if we have a calibration graph, we can get the unknown sample. All you have to do is place the blank sample, fix the wavelength, place the blank sample and set the absorbance value to 0. Now place the unknown concentration and note down the absorbance value, and from the calibration graph you can know the unknown concentration. This is how it is very useful for industries. There are many applications of this colorimetric analysis. We can analyze the concentration of iron, chloride, fluoride, manganese, zinc in water samples, nitrates, phosphorus, ammonia in fertilizers, soil samples, because in soil we are using fertilizers. How much of this ammonia is there, how much phosphorus, nitrates are there, because these are the most essential macronutrients in the soil. And we can also analyze the hemoglobin content in blood samples, color in beverages and food products, because we use a lot of colors in our food products. And it also monitors the growth of bacteria and yeast growth, which is also used in biological for biological applications. And colors used in printer toners, because we have plenty of colors and the intensity of color can also be analyzed using this application. That's all for the session. Thank you for listening to this, and subscribe for more informative videos. Until we meet in another session, bye bye. Thank you.